Hey everyone, this is Mr. Wilcox here, and I kind of wanted to start doing this other type of video. So here is with a document camera. So this is the document that I have made, and I'm hoping that this will be better. And if you guys could, please send me feedback on if you like this better than what we've been doing so far in class, and if you like the videos that we've been doing with the daily greetings, things like that. Okay? But for today, what we're going to be talking about is something called exponential growth. Okay, and we'll look at what the graph of exponential functions look like in the future, but really we should ask ourselves, well, what is exponential functions? And these are functions of the form y is equal to ab to the x power. So the x isn't being multiplied, it is brought to a power on b, okay? And we do have stipulations on a and b, okay? The only stipulation on a is a cannot be 0, because if it was 0, if a was 0, 0 times anything for b to the x would just make y 0. So if a was 0, it would make everything 0. Okay? Another stipulation is b has to be positive or greater than 0, and b cannot equal 1. And the reason why b can't equal to 1 is because let's think about it. If b was 1, well, 1 to any power, so 1 to the x power, or any power number we put in for x, so any number we put in for x, that will just make 1 to the x, well, just 1. And so all we would get out constantly would be y is equal to a. So these are just kind of eliminating kind of some unneeded or unnecessary responses that we're never going to hit. And we're just worried about anything. A cannot be 0, b cannot be 1, and b has to be greater than 0. Okay? And the important thing here is exponential functions are not linear functions. So if we are given a table of points, we will be able to tell if a table of points, so I'm telling you this is linear and this is exponential, we will be able to tell if this is linear. If I didn't give you this part, if I didn't give you the equation and I just gave you the chart, I could tell that that was a linear equation. And similarly here, if I didn't give you this equation, I can tell you that this is an exponential function. Okay? So well, let's look and let's say, okay, how can I tell which one it is? So we said exponential functions are not linear, so that must mean that it doesn't go up in a linear fashion. And really what that is, well, okay, what do I notice as my x's go up? What happens to my x's? -2, -1, 0, 1, 2, 3. What we're doing each time is, in essence, we're just adding 1 to our number. -2 plus 1 is -1, -1 plus 1 is 0, and so on. So really that's all we are doing to our x values. And if we notice it on the exponential functions, actually that's exactly what we're doing on this side too, is we're just adding 1 to our exponential functions on our x values. We're just adding 1, -2, -1, 0, 1, 2, 3. But where things get a little bit different now is what happens to our y values. Well, here I go from, okay, -4 to -1, -1 to 2, 2 to 5, 5 to 8, 8 to 11. And I think what's really happening here is really clearly seen on this later half. And so between 2 to 5, 5 to 8, 8 to 11, really what's happening here is I'm adding 3 to all of my numbers. I'm adding 3. And if we actually really looked at this, if we did this, 3 kind of came into our slope. Now there's a little bit more that comes into it, but it's really just this change of y is 3 over the change of x, which is 1. That gave me my 3 over 1, which gave me my 3 as my slope. Okay? And where we get this 2 from came from, well, let's check when x is 0. What's our y value? Well, y value is 2. That tells me that's where it's going to hit the y-axis at 0, 2. That is what we did with linear functions. And we are going to do something very similar now with exponential functions, where now let's say, okay, I'm adding 1 each time to my x values. But what am I doing to my y values? And again, just like with the linear function, I think it's easier to see what's happening here when we get to our later numbers. So here, 2, 6, 18, 54. What's happening to these numbers? Well, 2 to 6, it says, okay, I'm adding 4. 6 to 18, I'm adding 12, 18 to 54, I'm adding 36. That doesn't seem like there's a clear and consistent pattern. But what we notice is between 2 and 6, instead of adding 4, I'm actually really just multiplying by 3. 6 to 18, multiplying it by 3, and 18 to 54, I'm also multiplying that by 18. And so the clear difference between linear functions and exponential functions is linear functions, we add our y values over and over again, where exponential functions, we are no longer adding, we are multiplying our y values by some certain number. Okay? And again, what we're multiplying by, if we're going up by 1, is going to be this value here. And we can clearly see that. That 3 comes from this 3 here. This 2 is very similar to this 2. This 2 came from when 0 was x. What's my y value? Well, that's 2. Well, when 0 is x, my y value is still 2. So here, this 2 comes into play from this point right here. What happened when our x value was 0? My y value was 2. And so I've already kind of answered the next part and said, okay, well, we can use this table to determine the equation of an exponential function. We can do that. So I want to kind of give some background information first and say, okay, well, a in this equation, y is equal to ab to the x, or the exponential equation we had from the top, a is the initial value. A is the starting point. And again, just like how we have the initial value or our starting point in our lines, our starting point is when x is 0. Let's find what that y value is. So that a value for this equation is going to be 2, and we can clearly see that. A times b to the x, what's being multiplied to b to the x here? Well, what's being multiplied to 3 to the x? 2 is. So a is going to be that value of 2. Or a is that initial value. What happens? What's my y value when x is 0? Whereas my b value is the base of the function. And b is the base of the function, and really how we get this, and we've already explained this as well, and I'm re-explaining how a is known and how b is known, but b is the base of the function, and this can be seen by looking at what is happening to our y values as our x increases. So as my x increased by 1, my y values are being multiplied by 3. Okay? As my x values added 1, my y values is being multiplied by 3. So again, we find our a value at our table when we look at our x value being 0. Look at my y value, that is going to be my a value. So if I actually, let me grab something to kind of indicate this. This 2 here is this 2. Because I saw my x value was 0, so what was my y value at that point? And similarly, this 3 here is this 3. Oops, there we go. Now it's kind of hard to see, but it's y is equal to 2 times 3 to the x, and actually I will rewrite that above it so you can actually see what that original equation was. And this is just a helpful way of us being able to determine how did I get this 2 and how did I get this 3. And if you want to pause the video, here is a written description of how we find it. A is known as the initial value, and the initial value is seen on the table when x is 0. The value of a would be the y value when x is 0. So the y value when x was 0, and here b is the base of the function. This can be seen by looking at what is happening to our y values as our x increases. And so I do have two more questions. Okay? 2 more questions to go over. 1, write a function rule for this function of this table. Well, I'm telling you already, I'm going to actually zoom in a little bit more. I'm telling you already that this is an exponential function, and we can honestly see that by saying, okay, what is happening to my x values? Well, my x values are adding 1. Okay, and what is happening to my y values? And so I want to ask you is figure out what am I multiplying to each number to get the next number in the table? What's happening there? So I want you to take a few seconds, figure out what this number is, and then also see if you can figure out what the equation is based off of this number and the rest of the table. So take a couple moments, pause the video to figure out what the equation of this table is, and we will come back to it once you unpause and you're done. Okay, so pause the video and take some seconds just to do this. Take a few moments to do this. Okay, so what we realize is 3 times what gives me 9? Well, that's 3, and let's see if that's consistent. Is 9 times 3 equal to 27? It is. 27 times 3 is 81, and 81 times 3 is 243. So now it tells me, okay, now I just found my b value. My b value is this number that we're being multiplied by. That is my b value. Be multiplying that over and over and over again. Now the real question becomes, what is my a value? And remember, my a value is, tell me, I have to stop when I see x is 0. X is -2, that's not 0, -1. Oh, here is 0, so what's my a value? A value is going to be that y value, that 27. So now all I have to do at this point is just substitute the values into this equation. A is 27, B is 3. And this is the equation of this table. Okay. And one more example that I have here is to graph the functions of y is equal to 3 times 2 to the x and y is equal to -3 times 2 to the x, and compare the graph with y equals 2 to the x. Okay. Well, I do think this is a little bit easier here. Okay, if I do this function here, as I say, okay, what is y is equal to 2 times -2 to the -2 power? Well, if we review our rules for exponents with negative powers, this is going to be switching this to the reciprocal of 2 and taking it to the positive exponent. So now instead of it's 2 to the -2, it's 1 divided by 2 to the second power. And 1 divided by 2 to the second power, 2 to the second power is 1/4. Okay? At this point, this is honestly all you really need to know. Because at this point, I can just multiply by the base over and over again. Multiply by 2. Multiply by that b value. The b value here was what we were multiplying over and over again. So I'm going to do the exact same thing here. B is 2, so I'm going to multiply that over and over again. And say, okay, what's 1/4 times by 2? Well, that's a half. Because 1/4 plus a fourth is 2/4, which is a half. 1/2 times by 2 is 1. Which again makes sense because it says my a value is 1. Well, I have nothing being multiplied by 2 to the x, so we can have imaginary 1 there. 1 times 2 is 2. 2 times 2, that's 4. So this all makes sense. These are my points. -2 a fourth, -1 a half, 0, 1, 1, 2, 2, 4. Okay? And what we notice is there's actually a relationship between this and this. This function, this first function, and this second function. And what we realize is now no longer is it 2 to the x, but now it's 3 times 2 to the x. So really what I'm doing is taking 2 to the x and multiplying it by 3. So I'm taking this number and multiplying it by 3, and I get 3/4. And you can clearly see this is y is equal to 3 times, I don't know if you can see that because of my picture, y is equal to 3 times 2 to the -2 power. Well, this is y is equal to 3 times 1 over 2 squared, but we've already said 1 over 2 squared is a fourth, so this is 3 times a fourth, and 3 times a fourth is just 3/4. So 3 times a fourth is just 3/4. And so like I said, is all we're really doing is we're taking this number and multiplying it by 3 because that's what the rule says. Taking this and multiplying by 3 to get this. And so I'm going to continue doing that throughout. This is 3/2. 1 times 3 is 3. 2 times 3 is 6. 4 times 3 is 12. And we can clearly see that this function rule is still happening here. If I look at this base, I'm still multiplying by 2 throughout here. 3 times 2 is 6. 6 times 2 is 12. I'm still keeping this consistency of multiplying the base throughout. Whereas this last function is actually even easier than the last one, where I had to multiply by 3 to get this middle function. Now, I've got to just take this middle function and take the negative or the opposite of it. That's what this negative does. It's just, I have the middle function, 3 times 2 to the x, and now I'm just taking the negative of it. That's negative 3/4, negative 3/2, negative 3, negative 6, negative 12. And the last thing I need to do is I really just need to plot the points on the graph. So if I do this, I'm going to kind of do both these at a time. So if I do the first function, I'm going to do that function in purple, this purple that I have right here. Negative 2 1/4. So negative 2 about 1/4. That's a rough estimate where 1/4 is. Negative 1/2. 0 1. 1 2. 2 4. And what my function is really looking like is if I keep going forever and ever in the positive x direction, it's going to keep increasing on forever and ever. This is going to get huge as we get larger with x. Versus as I get more and more closer to the negative 10. The reason why this does never hit 0 is because this is a positive, right here. This is a positive number. 2 to any power is still going to be a positive number. It's just going to be a really, really small number. If I have 2 to the negative 100th here, if I put x is equal to negative 100, which is way down there, that's going to be equal to 1 over 2 to the 100th. And 2 to the 100th is just a really big number, but when I take 1 divided by a big number, that's just going to give me a really, really small number. It's still going to be positive, it's just going to be a small number. And so what we realize is as we keep going closer, as we keep getting more and more into the negative x direction, we will continue to stay positive, but that number is just shrinking and shrinking and shrinking. The number is shrinking, shrinking, and shrinking. So in other words, if we were to do a domain and range, well, my domain is my set of x values, and my x values continue to go this way forever and ever and ever, and continue to go this way forever and ever and ever. It just has to it's going to get there really slowly. So my range, my domain though, however, is I can put any x value into this equation. I can put any x value into this equation, and it'll just give me either a really big number or a really small number. It might give me a number that I have plotted here, but no matter what, I can put any x value in. And this is all real numbers, or I can put all real numbers here. That is my domain. I can put any x value into that equation, and we can see that because this keeps going forever and ever in the negative x direction, and this continues to go up forever and ever in the positive x direction. Whereas the range here, and I've already kind of discussed it and said, okay, well, the range for this function, it never hits 0. So it's every number above 0. So y is greater than 0. All my y values have to be above 0. Because it's never going to hit 0 because 2 to any power is going to still give me a positive number. Okay. Last two things I need to do is plot the last two functions. So I have two more colors I want to add in here. Here's blue and this is black. So we have blue and black. So I'm going to do the second equation in blue and say, okay, well now my function is negative 2 3/4. So negative 2 3/4, so a little bit above that. Negative 1 3/2. 0 3. So I'm looking at the middle column. So this is going to tell me my points here. My points here as I keep going down. So here, 0 3. 1 6. 1 6. And actually, I can't even plot this next point. 2 12. 2 12 is going to be off my graph. 2 12 is going to be way up here. Oops, I'm trying to get this to be fixed so you can actually, so it's not a little crooked. And what we realize is this function is actually growing a little more rapidly than the other one. Oops. And what we realize is forever and ever and ever, this is going to grow more rapidly, and it's going to be a little bit more compressed to this y-axis. Okay? But it's also being stretched on across the x-axis. The numbers at my 2 of my x-axis is a lot bigger as we keep going on and on forever. Okay. And last but not least, if I want to do this last problem, so I'm going to try to get this all in. Sorry if you can't see it all. But my last function is, okay, so I'm going to do this in black. This will be negative 2, negative 3/4. Negative 2, negative 3/4 is right here. Negative 1, negative 3/2. Negative 1, negative 3/2. 0, negative 3. 0, negative 3. 1, negative 6. 1, negative 6. And again, 2, negative 12 is not going to fit in my function, but I'm going to roughly estimate. And what this graph looks like is, in fact, it's going to go look like this. It's really just going to be reflected across this x-axis. It's going to be kind of flipped down instead of flipping up. And so this is what the key thing here. The key thing here is to compare functions, as well as also I think it's really important to be determined to how to write a function rule at the table, and then also to be able to determine, is a function a linear function or an exponential function. Okay, so please feel free at any time today, if you have any questions about exponential growth, please feel free to email me or use the discussion board. Again, this is just for exponential growth as we continue on. Next week, we'll be talking about something called exponential growth modeling, and then we're also going to be talking about exponential decay. So at any point, if you have any questions about today's lesson on exponential growth, please feel free to email me. And again, if you like this better than what the other videos have to offer, and the quality is a little bit better, let me know about the quality as well. Is the quality better than the daily greeting qualities? Please let me know this. Send me an email right away to see which one do you like better, so I can be consistent about what I do. Okay? And yeah, please feel free to email me with your questions, and thanks, and have a good day.